It's from fine to coarse-grained dynamic information flow control and back.
Okay. Hello, everyone. Can you hear me? No? No? Yeah? Better. Cool. So, thank you very much. Today I'm going to show that fine and coarse-grained dynamic information flow control systems are equally expressive. This is joint work with my co-authors. So at a high level, dynamic information flow control protects data confidentiality and integrity. To do that, we run a program with a security monitor that tracks information flows in a program and that stops the execution to avoid leaks. Now, in practice, there are many different ways to implement information flow control. And the two main approaches are fine and coarse-grained. These two approaches come from different community research, the programming language research and the operating system research. So in this work, we focus on formalization of these approaches. So in particular, we take the calculus from Austin and Flanagan for the fine-grained calculus and the one from Stefan and others for the coarse-grained. So information flow control system associate labels with data to protect confidentiality and integrity. So the label of a piece of data represents the sensitivity of that data. And the main distinction here between fine and coarse-grained stands in where those annotations are. So in the fine-grained system, the annotations are per value, whereas in coarse-grained systems, one single label protects the whole computation and is normally sufficient to protect everything in scope of that computation. People have claimed that the fine-grained approach is more permissive than the coarse-grained approach. And here with more permissive, I mean that they allow for more secure programs to execute, where the coarse-grained system instead might raise false alarms. Now, this work proves that that claim is false. We actually show that fine and coarse-grained dynamic information flow control systems are equally expressive. We do that with presenting a semantic-preserving program transformation between these two languages. All the results in this work have been formalized in AGDA and are available online. So this work has important practical implications because we show that coarse-grained information flow control can track information flows as precisely as the fine-grained approach. Secondly, these verified transformations allow the programmers to write programs in whatever style they feel more confident with, and then to run them on a system that works with the other approach. For example, the coarse-grained approach requires normally fewer program annotation in the fine-grained system, so a programmer might decide to write the program in coarse-grained style and then convert it to the corresponding fine-grained program. So in the rest of the talk, I'm going to present the two calculi, the fine-grained and the coarse-grained calculi, and their respective transformations. Now, since the fine-grained calculus is supposed to be more precise, I'm going to use the arch and arrow for fine-grained programs. Now, this program computes the sum of two numbers, and in the fine-grained system, those values are labeled. So here, I'm going to use L for low, that is a public number, and H for high secret. When we execute this program, the security monitor computes the sum of the two numbers together with the security label of the result. In this case, the label is secret because the result depends on secret information. Here is another example. The program tries to leak information about the secret, returning different variables. Those variables are mapped in the environment, and their corresponding value is also labeled. In this case, both of them are public values. To avoid leaking here, the security monitor features a program counter label which tracks the control flow dependencies. So what happens is that whenever we branch on a secret, the program counter rises to reflect that. And when we look up the value of that variable in the environment, it taints the label public with the program counter secret to reflect the fact that the result depends on secret data. Now I'm going to show you the coarse-grained calculus, for which I'm going to use the bomb as an icon. So the coarse-grained calculus uses monads to structure programs. In particular, in this calculus, the values are not labeled, but are protected by the current label, which is part of the monad. Then this calculus allows to manipulate secret values which are encapsulated in the labeled type, which is intuitively just a box that is labeled with the security label that represents the sensitivity of the content. Now, when we run the program, as I mentioned before, values here are not labeled, and the result 8 here is protected by the current label. The more interesting aspect is when it comes to the labeled type. So if we want to use some piece of secret information, we cannot simply branch on a box because it's a different type, but we first need to open the box with the primitive unlabel. The effect of that is to extract the content, but now that is going to taint the contents, the current label with the label on the box, to reflect the fact that now secret information is in scope. The problem is that when we open too many boxes, the current label rises, and then we cannot perform public side effects anymore. This phenomenon is called the label creep, and might actually end up resulting in false alarms. To avoid that, coarse-grained calculi features a two-labeled primitive, which creates a separate context where a computation executes. For example, here, the nested computation opens a secret number and increments it. So what happens is that the primitive creates a separate context where the current label might rise, but after the program is terminated, returns the result in a box that is labeled with the final current label. So observe here that at the top level, the current label doesn't rise. So this avoids getting tainted. Now let me get to the meat of this work. Let's see the first transformation. This is going to be from fine to coarse-grained. So intuitively, we want to define a program transformation that maps P to P prime, a secret value, in this case, to a secret box, and similarly for the environment. And we want to show that the transformed program executes and gives us the transformed result. It's important to notice here that the current label stays the same throughout execution. This simplifies the proofs, which then follows by induction. So let me sketch for you the translation. For values, it's very simple. All the values are annotated with a label, so we create a box with the corresponding label and the corresponding content. Then we do the same for algebraic data types recursively. Now, for programs, remember that in our theorem, we promised to never rise the current label. Therefore, we're always going to use two labels to avoid getting tainted. Then, since all the values are translated into the labeled data type, we have to use unlabeled to extract the content and then perform the computation. So if we want to add these two numbers, for example, 3 public will be mapped to this box and 5 secret will be mapped to the second box, and we extract their content and we compute the sum inside the two-labeled block. Now, the two-labeled primitive will produce a labeled box for us. And in order to prove semantic preservation, we have to make sure that the resulting label corresponds to the label that we would get from the fine-grained system. So in this example, it's easy to convince ourselves that that is the case. In particular, 8 at security level secret is transformed to the labeled box that contains 8, and this internal block results in a current label secret because we open the secret box. What I just showed you is the transformation from fine to coarse-grained, which essentially shows that the claim that fine-grained information flow control is more permissive than the coarse-grained approach is false. So in particular, I showed you that with our transformation, together with the semantic preservation theorem, coarse-grained information flow control can track information as precisely as the fine-grained approach. Now, let me go through the last transformation from coarse-grained to fine-grained. This is, interestingly, the part that is technically more challenging. Let me get to the point and show you what is the hard part here. So if we naively translate a program, we might have a mismatch in the labels. The program that we have here opens a public box, then opens a secret box, and returns the content of the public box, X. So here, this is the coarse-grained execution. So this is a coarse-grained program, and since at this point we open a secret box, whatever might follow might depend on the secret data. For this reason, the content of the box, which is X, and that came from a public box, gets labeled ends up in a box that is labeled with secret. Now, intuitively, what the program is doing is simply has access to variable X that contains 3 public and Y that contains, let's say, 5 secret, and just returns the first variable, which is public information. On the right-hand side, instead, we have a box labeled with secret, and therefore we would translate this with 3 at security level secret. Now, the translation is not semantics preserving because we have a mismatch in the labels. From the left-hand side, we get 3 public, and on the right-hand side, we get 3 secret. Now, the idea is to lose the precision of the fine-grained system in a controlled way systematically at runtime. For this reason, we use the primitive taint. This is a primitive that simply upgrades public data to secret, and it's a primitive that is completely safe, and it's a trivial extension to both calculi. So here is how it works for the fine-grained system, where 3 public gets upgraded to secret. And here's the one for the coarse-grained calculus, where the effect is instead to taint the current label and return unit. So this is the monadic primitive. If we inject taint in the appropriate places, we can lose the precision of the fine-grained system and recover semantic preservation. So in particular, here we taint X, the public data, with the label of Y. So label of is a primitive that I haven't presented yet, but it's a simple primitive that is useful in dynamic information flow control languages to project the security annotation on values, and it's useful in practice to write actual programs. So by tainting X with the label of Y, we can actually upgrade 3 from public to secret and recover semantic preservation. So combining the coarse to fine-grained transformation with the semantic preservation theorem, we can show that the fine-grained approach can simulate a coarse-grained approach. Now, the key insight is that we need to use taint and label off to lose the precision systematically as we need it. And in the semantic preservation theorem, we use a cross-language equivalence relation to relate the value that we get from the fine-grained language with the value that we obtain from the coarse-grained language. Now, there are more details in the paper, but I won't have time to go through them here. So let me quickly conclude with recapping what I showed you today. I presented a couple of semantic preserving transformation between fine and coarse-grained information flow control languages. These calculi are taken from literature, and they are sound, they are secure, and they satisfy termination-insensitive non-interference. I forgot to mention that the calculus features references as well, and they are in the paper. I was saying that these calculi are sound, they satisfy termination-insensitive non-interference, but we additionally prove non-interference in a different way using our semantic preserving translation. The idea of this result is to make sure that the transformation is authentic and is actually using the label annotation of the target language. Intuitively, the way it works is that if we want to derive non-interference for a source language, whether fine or coarse-grained, we apply our semantic preserving transformation, and then we apply non-interference of the target language, and then we back-translate the results to obtain and derive non-interference at the source level. Again, all these results have been formalized in Agda and are available online. With this, I conclude my presentation. I'm happy to take questions.
Okay, maybe a first question from Slido. So one of the questions was whether the two approaches have any non-functional differences, such as performance. If you could comment on that.
Right. Yes, it's possible. Yeah, I would say so, because the coarse-grained approach, it's a monadic approach, and I believe both in the number of reduction steps and also in the implementation as well, will the performance of that of the coarse-grained approach are likely more worse than the performance of the fine-grained approach. On the other hand, when we want to implement a fine-grained enforcement, that requires a lot of work, because we need to essentially modify the runtime system or the type system if we're doing a static enforcement. Whereas for the coarse-grained approach, we can the coarse-grained approach can be embedded as a library.
Are there any questions from the audience?
Do you think you can obtain a similar equivalence result for termination-sensitive non-interference, where the two-label construct is unsound?
So these two calculi are only satisfy termination-insensitive non-interference. So I'm not aware of a fine-grained calculus that is termination-sensitive. There are coarse-grained calculi that are termination sensitive. And intuitively, the reason is that in the termination sensitive coarse-grained calculi, they remove two-labeled, because two-labeled is vulnerable to termination attacks, because it has to wait until the computation terminates to label the box, and replace that with features, primitives like fork. Instead, in the fine-grained calculus, two-labeled is essentially hard-coded in the semantics itself.
Hi. Your fine to coarse-grained translation, it struck me that it looks kind of like a CPS transformation. Did you notice this too?
I wouldn't know, to be honest. I haven't looked into that.
I actually have a question. So you've probably chosen two specific calculi, but over the years there's been probably hundreds of information flow calculi defined. And so I was wondering if you had any sense about whether or not this result is robust to various extensions, perhaps dependencies like we saw in the last talk, or other features. What's your intuition there?
Right, so these work models, for instance, references, and these are flow insensitive. So the label on the reference stays the same. It would be interesting to look as an extension to this work what happens when we have flow sensitive references, so where the label annotation on the reference is allowed to increase during the execution of the program. So we believe that for other flow insensitive features could be handled just like we do here. For the flow sensitive, it's still an open question. I think that in the static, so there has been a previous work that did the same with the static enforcement, so static type system, and I think that there they also we're showing that for a calculus where it features similar to the flow sensitivity, they had the proof was much harder, and they had to restrict somehow the language. So it's a good open question for the dynamic calculus.
Let's thank our speaker one more time.